Let's look at a slightly more complicated system now. We're going to look at a second order system. We've looked at zero order and first order systems, and let's take a look at second order systems. Now, as you would imagine, in a second order system, the equation becomes slightly more complicated, and we don't just have a first differential of y in the equation, but we also get a second differential of y. Okay, and that's why we call this a second order system, because we have the second differential in the equation. Of course, my guess is that you have already done how to solve second order differential equations, and we will not go there, but let's look at some characteristics of such sensors. So if you look at the frequency response and try to look at y over x, what you would find is you can get an equation like this, where there are some parameters that we have already looked at. As you can imagine, in this case, we have three parameters that define a second order system. We have K, which is the static sensitivity, which is very similar to the kind of uh, parameter which we saw both in the zero order and the first order systems. In addition, you have two more parameters. You have the natural frequency of the system, or it's also called the undamped natural frequency of the system, and we have the damping ratio. Okay, so these three parameters together can define any second order system. So you may ask, well, where do we see second order systems? Well, here's an example. Think about this sensor. Now, this is basically a weighing scale. Uh, so it is connected to a fixed place, let's say a ceiling of a place or some fixed structure, and there is a plate that is connected with a spring to that fixed quantity. Now, depending on the weight that we put on this plate, the spring is going to extend or contract, right? So if you put a weight here, this is going to contract. If you take away the weight, the spring is going to pull the plate back up. And if we measure the displacement from this point to the plate, we will be able to measure the weight of the substance that you're putting on this plate. So that's what the sensor looks like. Now, what do you think the behavior of this sensor would look like if you took a 1 kilogram weight and put it suddenly on the plate? Okay, you just so there was no weight on the plate, and suddenly you put a weight on it. So what's going to happen? In many cases, what would happen is the plate would go down, and it would go beyond the final value, and then go up, and then it will keep oscillating and slowly settle down in its proper value, right? So you put a weight and it just goes like that. Okay, so that's a second order system. So let's take a look at a testing of the second order system and what happens when you give some kind of test signals to it. So what we do again is very similar as in the previous cases. We give an input which is a step input. So we suddenly change the weight on the sensor, and we don't have just one kind of response. Remember, in the first order system, depending on the time constant, we had different responses. So similarly, in this case, depending on the natural frequency and depending on the damping ratio, you can have different kinds of response. Okay, so if the damping ratio is above 1, what we have is a response that looks very much like the first order response. You have a slow rise and a settling down at its final value. If you have the damping ratio which is equal to 1, the same thing happens, but it is faster. This is the fastest first order like response that you can get here. But if the damping ratio is less than 1, what happens is you get some oscillatory behavior that we were talking about. Okay, so the final value is this, but the output does not settle on its final value. It overshoots it, and then it undershoots it, and slowly these oscillations keep reducing till after a certain period of time the sensor settles down at its output value. Now the speed of these oscillations is given by the natural frequency of the system. Okay, so that's how the damping ratio and the natural frequency works. So let me just kind of summarize that. If you have a damping ratio of greater than 1, you have no oscillations, you just have a slow rise and you go to the final value. If you have a damping ratio of less than 1, you have a very fast rise, and then you have these oscillations, and then you settle down at your final value. So that's the response to a step input. What happens if you give a sinusoidal input? What you would see is that here the x-axis is frequency, and as you change your frequency, again, if the damping ratio is greater than 1, you have a first order like response, basically a low pass kind of characteristic. So the sensor behaves like a zero order system for very low frequencies, but as the frequencies get higher and higher, the sensor is not able to keep up with the change, and the gain becomes smaller and smaller. If the um, if the damping ratio is less than 1, then what we get is we would have a ideal response for very low frequencies, but as the frequency increases at a particular frequency, you get an output which is actually larger than the input. You get a gain that is greater than 1, and then if you keep increasing the frequency, the gain goes below 1. So that's how a second order system behaves.